Hello, welcome to the introduction to our poster on a probabilistic framework for the integration of mass spectrum and retention time information in small molecule identification. My name is Eric Bach. I'm a PhD student at the Aalto University in Finland, and I'm going to talk you through the poster that we present in a high level, and I will be available for live discussion during the session, and you can ask questions then for details. So let us start here with section 1, which introduces the context in which our work is in. We are in untargeted metabolomics, small molecule identification, and here the task is to find out what kind of molecules you might have in a biological sample. We consider the case that you analyze your data with liquid chromatography, tandem mass spectrometry, LC-MS, but we also tackle the case that maybe you don't have tandem MS information for all the MS features in your dataset. So the main focus of our work is how do you actually utilize the LC retention time information. As we know, it can aid the small molecule identification by giving you additional information next to the mass spectrometry data. There are a couple of challenges in utilizing retention time information. For example, retention times are liquid chromatographic system specific. It means they differ between different configurations of your LC column. Typically, reference databases are limited in size and molecule coverage, so maybe in your laboratory you have only measured like for a couple hundreds molecules reference retention times, and the mapping between different LC systems of retention times requires you to have at least some kind of overlap. So the basic workflow is given here. So we have biological sample, your LC-MS2 system, and then you have this LC-MS spectrum, you have the features. For some of the features you also have the tandem mass spectrum. So what's the framework that we now propose? So it's a probabilistic model with an efficient inference that makes jointly use of mass spectrometry information and retention time information. The mass spectrometry side is kind of up to the user. That means the way you exploit the MS information, so what kind of scoring you use for the MS data, let it be MS1 or MS2, is up to you. We do not require you to have any reference retention times for the target LC system available. And the output of our framework is like a ranking of molecular structures in what we call molecular candidate sets. That means you have for each MS feature a set of potential molecular structures that could be the identification, for example, based on exact mass search. The key is that we, instead of exploiting directly the retention time information, we resort to use the observed retention orders in your LC-MS data. That means up here in figure number 1, you see you have the features, they occur in a certain retention order, and we exploit the observed retention order combined with predicted retention orders to up or downvote the molecular candidates in your candidate sets. Here in section 4, we present our probabilistic model to integrate the different sources of information. So it's a Markov random field, a pairwise Markov random field where the node scores encode the MS information and the edge scores encode the retention order information. So maybe I should say the nodes correspond to the MS features, edges correspond to the feature pairs. And we use so-called max marginals to rank molecular candidates, which means that we compute the probability of a certain molecular candidate assigned to a certain feature given all the other data integrated through this Markov random field. So a key point here is how do we exploit the retention orders. So for that we look at the observed retention orders, which is here in section 5, in this equation given like the difference of the observed retention times, the sign of it tells us in which order we have observed two features, and then we use a predictive model for two molecular candidates that are associated with two features to predict what would be their retention order. And if these two things agree, the observed and the predicted retention order, then we basically give a higher score to these two candidates. Another important aspect of the work is that we had to figure out how to do a feasible inference. In practice, these pairwise Markov random field, if it's based on a complete graph, the inference is kind of intractable because of the large space of the possible labels, so the candidates. So what we do is we resort to an inference over a random subset of random spanning trees. That means that for a set of spanning trees, we solve the max marginal computation, which can be done efficiently, and then we aggregate those max marginals, and that's described here in section 6. So just a few words to the results. We evaluated this on MassBank data, CASMI 2016, and also another dataset from MassBank, and we can observe that our score integration framework can basically significantly outperform the metabolite identification performance compared to only using MS information in different setups here described in experiment 1, 2, 3. Thank you for your attention, and please come to the poster and I will answer you all your questions and give you further details. Thank you.